In this video, we're going to talk about some important facts about linear independence, and then we're going to go through some examples to illustrate some of these facts. So let's go through the list. So for the first one, we have that any set containing the zero vector is linearly dependent. Next, any non-zero vector on its own is linearly independent. And the key here is that it's a non-zero vector, since the zero vector on its own is linearly dependent. Next, we have a very important example. So recall the standard unit vectors E1 up to En in Rn. These are the vectors that have zeros in all entries, except in one entry there is a 1. And the subscript tells us which entry that 1 is in. Well, the standard unit vectors are linearly independent. Let's take a look at an example. So in R3, we have 3 standard unit vectors, E1, E2, and E3. And if we want to show that they're linearly independent, then we take a linear combination of these vectors, so A times E1 plus B times E2 plus C times E3, and we set it equal to the zero vector. And now we're going to solve this. And so here we have that, looking at the first entries, that A plus 0 is equal to 0. So A is equal to 0. And now next we have 0 plus B plus 0 is equal to 0. So B is equal to 0. And finally, 0 plus C is equal to 0. So C is equal to 0. So the only solution to this is the trivial solution 0, 0, 0. So this tells us that these vectors are linearly independent. Now, the definition of linear independence that we used here is very useful for helping us to prove that vectors are linearly independent, but it doesn't really help that much in terms of gaining an understanding of what it actually means for vectors to be linearly independent. So hopefully these next 2 points will help. So vectors U1 up to UK in Rn are linearly independent if and only if none of the vectors can be expressed as a linear combination of the others. And the key here is that none of them can be. So for linearly independent vectors, none of the vectors can be expressed as a linear combination of the others. There's no relationships, no linear relationships between the vectors. They're completely independent. Whereas vectors U1 up to UK in Rn are linearly dependent if and only if at least one of the vectors can be expressed as a linear combination of the others. So there is a linear relationship amongst the vectors. There are dependence relationships amongst the vectors. So for dependent vectors, at least one can be expressed as a linear combination of the others. They're dependent. At least one is dependent on the others. So we, in the previous video, did an example where we looked at these 3 vectors and found that they were linearly dependent. And in the first video, we actually did this using the definition, and we found a non-trivial solution to the equation that we were using. So I'll remind you there we had that 1, 2 minus 2, negative 1, 3 plus negative 3, 4 was equal to 0. So we had determined this non-trivial solution to the equation we were working with. And so once we have this non-trivial solution, what we can do is we can solve for any of the vectors that has a non-zero coefficient. So for example, we can solve for this one. So here, if we solve for 1, 2, then we obtain that 1, 2 is equal to 2 times negative 1, 3 minus negative 3, 4. So 1, 2 is a linear combination of the other two vectors. So these are dependent vectors, and what we've done is expressed this one as a linear combination of the others. And if we have this linear combination, we could bring all of these vectors back over to the other side and obtain, again, a non-trivial solution. So we bring them all over and leave the 0 vector on one side to obtain, again, a non-trivial solution to that initial equation that we were working with. And so for dependent vectors, again, the key thing to keep in mind is that at least one can be expressed as a linear combination of the others, whereas for independent vectors, they're completely independent of each other. None of them can be expressed as a linear combination of the others. So now, a special case of these 2 points is when we consider what happens with just 2 vectors. So if we have 2 vectors, then actually we can tell right away whether or not they're linearly independent, because they're linearly independent if and only if they are not parallel. So in other words, neither is a scalar multiple of the other. So if you have 2 vectors, then you can check quite quickly if they're linearly independent or not. If they're parallel, then the 2 vectors are linearly dependent. And if they're not parallel, then the 2 vectors are linearly independent. Okay, so we've got a few more points here. So now we're going to let U1 up to UK be linearly independent vectors. So we're going to start with a set of independent vectors. And we're going to let V be any vector. And for this point, the rule is that the set of U1 up to UK, including V, this new set that we've just formed, these are linearly independent if and only if V is not in their span. So this is what we're going to, this fact we will use to extend linearly independent sets. So if you have a set of linearly independent vectors, as long as you choose a vector outside of their span, then the new set you've created by adding that vector will still be linearly independent. Now we'll use this fact a little bit later in the course when we start talking about bases. Next, we have that any set of k vectors in Rn is linearly dependent if k is bigger than n. And this is a really nice one to keep in mind. If you have too many vectors, so in other words, if you've got more than n vectors in Rn, then that set is automatically linearly dependent and you have nothing to check. You just know that more than n vectors in Rn are automatically linearly dependent. And the last one here, so if you have a set of independent vectors, U1 up to UK, then any subset of these vectors will also be linearly independent. So for example, if I choose, let's say U1, let's say if k happened to equal 5, then I would have U1, U2, all the way up to U5 is linearly independent. And I can choose, so this is, let's say, linearly independent. Then any subset, and what I mean by that is I can choose any of these vectors, and as many as I like, so I could choose 4 of them, I could choose 3 of them, I could choose 2 of them, and any 2, any 3, any 4. So let's say we choose 3 of them. So let's say we choose, let's say U2, U3, and U5. Then this subset of this bigger set is still linearly independent. So if you have an independent set of vectors and you remove vectors from that set, then the smaller set is still linearly independent. But that's not necessarily true the other way. So this is still linearly independent. So if you have an independent set and you shrink it, then the new set is still linearly independent. And the thing to keep in mind with linear independence is that any time you change the vectors involved, you have to reevaluate whether or not the vectors are independent. Independence is not a property of an individual vector. It depends on which other vectors that vector is grouped with. So in some sets, a specific vector will form a linearly independent set, but paired with other vectors, then that vector could be involved in a linearly dependent set. So anytime you change the vectors involved, you need to reevaluate whether or not those vectors are still linearly independent. And so in this case, if you remove vectors, it turns out they're still independent. And here we saw how to enlarge the set. If you have independent vectors, as long as you choose something from outside the span, then the new set will remain linearly independent. So these are the facts that we're going to go through. And so now let's go through some examples. All right, so we won't go through all of these examples in this video. I'll do one more video where I finish off the last two examples, but we'll start here. And I do encourage you to try these examples on your own. See if you can figure them out first. So if you want to pause the video, you also have the slides, so you can try them on your own first. But for each of the following sets of vectors in R4, we're going to determine if the vectors are linearly independent. And at the same time, we're also going to revisit the concept of span. So we're going to look at both of these together. Often we do consider these properties together. So a little bit of review on span here as well. Okay, so let's start with these vectors here. So here we have U1, U2, and U3. And the first question is, are they linearly independent? And so now what we're going to notice by looking at this is the answer is, right away, the answer is no. And the reason that I can say that right away is that this set contains the 0 vector. And we know that any set containing the 0 vector is linearly dependent. So the answer is no, and the reason is any set containing the 0 vector, well, let's just put containing 0, is linearly dependent. Okay, so now let's ask if they span. So can these vectors span R4? And the answer is also no. And if we think back to the properties of span, the property we're going to use here is that here we only have 3 vectors, but we're asking if they span R4. And the key is that 3 vectors cannot span R4. So the reasoning for saying no here is that 3 vectors cannot span R4. So here, 3 vectors cannot span R4. So you need at least 4 vectors to span R4. If you have fewer than 4 vectors, they can't span R4. Now this example actually gets a little bit worse because here we have the 0 vector. And so here, what we're actually considering is the span. If we look at the span of these vectors, so we have the span of U1, and then here this is 0, and U3. And we know that if one of the vectors is a linear combination of the others, so 0 is certainly a linear combination of the others, that we can actually remove it as one of the generators here for our span. So we know that the span of U1 and 0 and U3 is just the span of U1 and U3. And we can also just think about this. If we take all possible linear combinations of U1, 0, and U3, the 0 is not contributing anything. Anything we could make out of all 3 of them, we could have just made out of these 2. 0 doesn't contribute anything. Any scalar multiple of 0 is just 0. And so certainly the span of all 3 is just equal to the span of 2 of them. So in this case, not only are we looking at the span of 3 vectors, in fact, we're just looking at the span of 2 of them. And certainly 2 vectors, again, cannot span R4. So it was true already with the 3, but in this case, remember, we can remove the 0. The 0 is contributing nothing in terms of generating. We're not removing it from the span. It's still in the span. We're just removing it as one of the generators of that span. So it's any linear combination out of all 3 is just a linear combination of these 2. So 0 is still inside this set. We're just not taking it as one of the generators. Okay, so the next question here. So here we have a single vector. And again, we're going to ask the same thing. Is it linearly independent? And the answer is yes. And the reason that we know this is that any vector, which is not 0, so any non-zero vector is linearly independent. Okay, and now, does it span R4? Well, again, the answer is no. We only have one vector, and again, you need at least 4 vectors to span R4. Fewer than 4 vectors cannot span R4. So in this case, the answer is no. It's not going to span R4. So one vector cannot span R4. You have to have at least 4, but again, you have to be a little bit careful. Just because you have 4 vectors in R4 does not mean that they will span. You have to actually check that. But right away, if you have fewer than 4 vectors in R4, so fewer than n vectors in Rn, then they cannot span. Okay, so let's move on to our next page here. Okay, so here we have the vectors u1 up to u5. And again, we're going to ask the same question. Are they linearly independent? And this time, we're going to say no right away as well. And so what fact are we using here? So the answer is no. And in this case, the problem is that we have just too many vectors. So again, remember when you're in R4, if you have more than 4 vectors, so in this case 5, more than 4 vectors are automatically linearly dependent. You don't need to check. So the key here, the reason is that 5 vectors in R4 are linearly dependent. Now, if you have 4 vectors or fewer, they may or may not be linearly independent. You have to check. So we can only automatically eliminate them if we have more than 4 vectors in R4. If we have 4 vectors or fewer, then we actually have to check. We can't just declare right away if they're independent or not. But if we've got more than 4, then automatically they're not. Now for span, this one's a little bit tricky. We have 5 vectors in R4. So 5 vectors in R4 may or may not span. We do have to check. Certainly if we had fewer vectors than 4, we could say they don't. But in this case, we have 5. But what we're actually going to notice here is, now this, if we look here, what we notice is that in this case, all of the 4th entries are 0. And so if we think about taking, with span, we're taking all linear combination of these vectors. Any linear combination of these vectors will always end up with a 0 in the 4th entry. So any vector that does not have a 0 here cannot be expressed as a linear combination of these vectors. So the answer is certainly no. And for example, if we take E4, so E4, remember, is the vector, so 0, 0, 0, 1. This vector, because there's a 1 here, you cannot express this as a linear combination of these vectors. Any linear combination will have to end up with a 0. And so what this says is that E4 is not inside the span of these 5 vectors, so U1, U2, U3, U4, and U5. So if there's a vector that's not inside their span, then this cannot be everything. If it was everything, then it would mean all vectors would be in there. We found something that's not in there, so it's not everything. So our conclusion here is that the span of these vectors, so u1, u2, u3, u4, and u5 is not equal to R4. We found something that's not inside the span, so it can't be everything. There are vectors that are not in there. Okay, and so for this video, we'll do one last example. And so we have these 4 vectors here, and again, we're going to ask exactly the same question. So are they linearly independent? Now, again, in the previous example, we had too many vectors. If you have more than 4 vectors in R4, then they're automatically dependent. But if you have 4 or fewer, then you have to check. So we can't just automatically say whether they are or not. But what we're going to notice here, if we look at these vectors carefully, is that u4 is actually 2 times u1. And so this actually tells us that this vector is a linear combination, certainly of this one, but it's actually a linear combination of all 3 because we can use 0 as the coefficient. That's okay, as long as at least one of the coefficients is non-zero. So what we found is that this vector is a linear combination of the others, which says that this set is linearly dependent. One of the vectors is a linear combination of the others. So the answer here is no. And the reason it's no is u4 is equal to, so again, it is just equal to, in terms of this is 2 times u1. But like I said, we can add 0 as the coefficient on the others. So it's going to be 2 times u1 plus 0 times u2 plus 0 times u3. So this vector is a linear, at least one of them, you have to have a non-zero coefficient here somewhere. Well, that's not true. If you have the 0 vector, it is a linear combination. If all coefficients are 0, you're going to get the 0 vector. So the 0 vector is always a linear combination of all other vectors just by taking the coefficient to be 0, but this thing is non-zero. So here we do have a linear combination. The key is that you're allowed to use zeros if you need them. So in this case, we have this vector is a linear combination of the others. And so what does this tell us? So let me write that down again. So this says that U4 is a linear combination of the vectors here u1, u2, and u3. And so this tells us, using one of the facts on the previous page, that the set u1, u2, u3, and u4 are linearly dependent. So if one of the vectors can be expressed as a linear combination of the others, and again, it's okay to have, strictly speaking here, this is just, it's parallel to u1, it's a scalar multiple of u1, but I can add 0 coefficients to bring in the other ones. Again, like I said, if all coefficients are 0, you're going to get the 0 vector, so the 0 vector is a linear can be expressed as a linear combination of all sets of vectors, but in this case, we can certainly, we've got u4 is 2u1 and add the 2 0 coefficients there. So it is a linear combination of all of them. And so they are linearly dependent. And now the last question, do they span? We've got 4 vectors in R4, so we can't just automatically, if we had fewer than 4 vectors, then the answer would be no. If you've got 4 or more, you actually have to check. And the answer here, again, we're going to use that fact, we're going to use the fact that one is a linear combination of the other. So the answer will be no. And so here we have no. And since u4, again, is equal to 2 times u1 plus 0 times u2 plus 0 times u3. So since we have this, if we take a look at their span, So if we take a look at all linear combinations of all 4 of these vectors, all right, so what is the span? So when we ask if they span R4, what we're asking is what is the span of U1, U2, U3, U4 equal to? So is this thing equal to all of R4, or is it a smaller object? Well, in this case, because U4 is a linear combination of the others, we know that span of U1 up to U4 is actually just equal to the span of U2, U3, and U4. Anything we can make out of all 4 of them, we can just make out of the 3 of them. Because U4 is already a linear combination of the others, we can remove it as a generator. Any linear combination of all 4 of them can be expressed as just a linear combination of these 3. So again, this is a nice thing to keep in mind when working with span. If one of your generators here is a linear combination of the others, you can remove it. It's still in the span. It's still, U4 is still inside this set, we're just not taking it as one of the generators. So any linear combination of all 4 is a linear combination of just the 3 of them. So I didn't need this vector because anything I can make out of all 4 using scalar multiplication and addition, I could have made out of just 3 of them. And so now we have the span of these 4 vectors is actually just the span of 3 of them. And what do we know about 3 vectors? 3 vectors cannot span R4. And so here we have and 3 vectors cannot span R4. So this is a nice example in that it uses a couple of the different properties of span, a couple of nice things to keep in mind. If one vector is a linear combination of the others, you can remove it as one of the generators. Like I said, it's still in this set. Span is all possible linear combinations, so U4 is still in here. And then the other result is that if you have fewer than vectors in R4, then they can't span. So 3 vectors cannot span R4. So I will stop the video there, and in the next one I will do 2 more examples.